All right, we're looking at lesson 2.2. So we're going to explore some polynomial functions and their graphs. A polynomial function is when n is a non-negative integer, and we have a sub n minus 1, all the way down to a sub 0, and they're all real numbers. We can define a polynomial function in this fashion, that f of x equals a sub n times x to the n. All right, so you have some kind of real number coefficient on a variable raised to an exponent, and then it keeps adding on the next real number coefficient, x to a the next lowest consecutive exponent, and so forth, all the way down to a constant at the end. Now, you don't need to have every single term there because your coefficients might be 0, so you may not have every exponent on x, but basically, it's the adding and subtracting of terms where you have x's raised to any exponents as long as they are positive exponents, and you have coefficients that are real numbers. All right, we call this a polynomial function of degree n, so the highest exponent is the degree, and the number a sub n is the coefficient with the highest power. We call that the leading coefficient. Okay, so if you remember from last year, you talked about degree and leading coefficients, and that tells you a lot about their functions. So just a couple of little review, like if you had f of x equals some real number coefficient and times x to the squared, x squared, you would call that a quadratic, which we just reviewed yesterday, because it's degree 2. If you have f of x and it's just a times x to the first, that's linear because it's degree 1. We had cubics we've seen in the past, f of x equals a times x to the third. We also have quartics. You dealt with those last year as well. Anything else, we call it degree 5, degree 6, degree 10, okay, is however the highest exponent is. All right, so polynomial functions, they are smooth and continuous. All right, there's no breaks in the graph over here. There's no sharp corners. Okay, these are not polynomial functions. Here, these are polynomial because they're smooth, rounded as you turn, okay, at maximum and minimums, whether they're relative or absolute. Okay, so things you should recognize. All right, and behavior. So we did talk about this last year, but a little review of it. So as x increases or decreases without bound, the graph of the polynomial function will eventually rise or fall. So we look at the ends, okay? Not so much in the middle when we're looking at end behavior here. All right, when n is odd, so if you have odd degree, you will either have ends that rise to the left, fall to the right, or fall to the left, rise to the right. Okay, if the leading coefficient is positive, the graph falls to the left, rises to the right. So it starts low, ends high. So that's for a positive leading coefficient. If you have a leading coefficient that's negative, the graph rises to the left, falls to the right. Rises to the left, falls to the right. Again, we're talking just the ends. When your degree is even, both ends go in the same direction. All right, so if your leading coefficient is positive, the graph rises to the left and rises to the right. Again, we don't care so much right now about what's going on in between there, but just at the ends. And then if your leading coefficient is negative, but your degree is even, it falls to the left and falls to the right. Okay, we're talking at the ends on these. All right, so that's all, you've done that in the past. So we're going to review it a little bit here. All right, using the leading coefficient test. So using this test, determine the end behavior of the graph. All right, so if we look, there's your highest degree. So the degree is 3, which is odd. The leading coefficient is positive because it's 1. So if you have an odd degree and a positive leading coefficient, your ends should look like this, right? It should fall left, rise right. And just verifying that, here's your graph. Falls left, rises right. All right, another way you could see this written as x goes to negative infinity. So as we're going further on the left side of the graph, as x is going to negative infinity, f of x also goes to negative infinity. And as x goes to infinity, f of x goes to infinity. Just another way to kind of write it, but it falls left, rises right. We'll skip that one for now. All right, putting it to a word problem. It says use end behavior to explain why this f of x is only an appropriate model for AIDS diagnoses for a limited time period. Well, if we look at this function, there's our term with the highest exponent. So we have an odd degree with a negative leading coefficient. So if that's the case, our n's should rise left, fall right. Okay, so odd degree, negative leading coefficient. So it should rise left, fall right. Well, it says, why is it only appropriate for a limited time period? Well, because after a certain amount of time, if you threw this on a graph, this is going to decrease forever and ever and ever. So after, and we're not, looking specifics here, after a certain amount of time, this function would actually say that basically the AIDS diagnosis would go negative, right? And negative 1 million, negative 100 million. That should say time. The number of AIDS diagnosis. Which can't be the case, right? It could go to 0, which would be fantastic, but it can't go negative. Okay, so we would look at it only for a specific amount of time. All right, when we're talking about polynomial functions, you want to also talk about their zeros. All right, so a polynomial function where the values of x that give you f of x equal to 0. So when f of x is equal to 0, you find your zeros. All right, these values of x are called the roots or solution of the polynomial function equal to f of x when the equation f of x is equal to 0. Each real root of the polynomial equation appears as an x-intercept. So a real root of a polynomial equation appears as an x-intercept on the graph. All right, so here we've got a function f of x. We're going to find all of the zeros, and then we're going to just verify it with the graph. So when you are finding them, you set your equation equal to 0. All right, and we're going to factor this. So keep it equal to 0. We can group it, take out an x squared, take out a -1. So I'll have x plus 3 times x squared minus 1, which is a difference of perfect squares, so you can factor it further. So now each one of those gets equal to 0, and we would know that x is -3, x is -1, x is 1. And if you look at our graph, 1, -1, and -3. So those are your x-intercepts because they are all real. All right, remember your degree tells you the number of zeros you should have. Not whether or not they're real, but how many zeros you should have. All right, and we'll leave this one. Next, here we got a quartic. All right, so degree 4, that means we should have 4 zeros. So let's set our equation. That's also a good thing to always note. That way you know that you found them all in the end. All right, so first thing I'm going to do is take out a negative x squared. All right, that trinomial can be factored further into x minus 2, x minus 2. So if we set these equal to 0, x squared equals 0, x minus 2 equals 0, and x minus 2 equals 0. So you get x equals 2 twice, and we'll discuss that in a second. And then x squared equals 0. So that means x equals 0, but twice. So if you remember from last year, first off, let's look at the graph. You have an x-intercept of 0 and 2. But notice here we've got, instead of like the last graph, they passed right through the roots. Here it bounces at the roots. So if you remember, because it shows up twice, we say that it has a multiplicity of 2. Same thing for this one, multiplicity of 2. And when your multiplicity is even, your graph will bounce at the x-axis. So if a root has an even multiplicity, it touches the x-axis and turns around. If a 0 has an odd multiplicity, it crosses the x-axis at that root. All right, regardless whether the multiplicity is even or odd, it will flatten out when the multiplicity is greater than 1. All right, so even if it bounces, it might flatten more if your multiplicity is 4 or 6, or if the multiplicity is 3, it will pass through, but it'll flatten at that. All right, so come tomorrow with questions, and we will try some of those problems.